Welcome to The Explainer. So, today we are tackling a truly mind bending concept that challenges pretty much the very foundations of computational geometry. We're going to be looking at a fascinating framework called the OMI protocol. And honestly, it introduces an absolute paradigm shift in how digital systems handle reality using something called deterministic incidence geometry. It's just a completely fundamentally different way to think about how computers draw the digital world.
I want you to start by asking yourself this. What if everything we know about how computers render foundational constants, things like pi and phi, what if it's entirely backwards? I mean, in most digital systems, we treat these mathematical constants as the ultimate, unbreakable laws of the universe. But today, we're going to treat this like an intellectual mystery. What if these constants aren't the rules at all, but merely the downstream byproducts of a deeper, hidden geometric logic?
All right, Section 1, Geometry's Floating Point Problem. Okay, let's dive into this by looking at the technical boundary problem of our current rendering systems. You see, most computational geometry starts with a pretty massive leap of faith, which is the traditional coordinate tuple of x, y, and z. Software basically just blindly trusts this value to define a solid shape. If it needs to rotate that shape, it imports a trigonometric constant. If it needs a sphere, it imports pi. It's efficient, sure, but, well, it actually creates a massive foundational boundary problem.
Which really leads us to the fundamental question here. What is the actual authority of that value? Like when you import a floating point approximation of a constant to build a deterministic digital reality, are you really building something mathematically exact? For a visual renderer, an approximation is perfectly fine, right? It just needs to look good enough on your monitor. But for a deterministic protocol, accepting a geometric fact just because a floating point calculation says so, that means you've given the drawing the ultimate authority over the math itself.
So the OMI protocol solves this by splitting constants into two entirely distinct categories. On one side, you have protocol constants. These are stored values treated as foundational authority, which, as we just discussed, is the old, flawed method. On the other side, OMI introduces projection constants. Now, these are values produced only after the underlying geometry has been strictly mathematically validated. In OMI, constants like pi or a square root should never, ever be foundational rules. They should only emerge at the display boundary. And this simple split, it literally eliminates the fundamental errors hiding in the code. Moving on to Section 2, Relationships over Coordinates. And this brings us to the real core paradigm shift of OMI, which is stopping our reliance on spatial coordinates altogether and instead strictly mapping relationships. In the old system, the primitive question was always, where is this point? But asking where relies on subjective, sloppy, approximated drawings within an artificial coordinate grid. It's essentially a localized illusion.
OMI throws that out entirely. The new primitive question is, what is this point incident with? It doesn't care where it is on a grid. It cares how it relates to everything else around it. A line isn't a drawn segment anymore. It's a relationship between points. A solid isn't a list of coordinates. It's a balanced structure. This is a legally binding, mathematically checkable contract.
And this brilliantly illustrates the golden rule of the OMI framework. Incidence defines geometry. Projection displays geometry. Coordinates and floating point math might still exist to help draw the picture on your screen, but those are just visual adapters. The true foundational authority is the incidence, that underlying network of relationships. Let's look at Section 3, the first exact relation. So if we aren't using coordinates, how do we actually build our first 3D object? Well, we use the tetrahedron, which OMI considers the very first exact relation. Notice how we define this sturdy, self-dual building block using an incidence matrix that is completely devoid of spatial coordinates. Vertices, edges, and faces map perfectly against each other in this grid. 4 vertices, 6 edges, 4 triangular faces. It perfectly balances to create a solid without a single x, y, or z coordinate ever being mentioned. No way, right? But it works. The math here validates itself flawlessly, kind of like an ironclad receipt of geometric reality. Each vertex touches exactly 3 edges. Each edge touches exactly 2 vertices. Each face has 3 vertices, and each edge belongs to 2 faces. The relation balances mathematically. This is what true deterministic geometry looks like at its absolute core. Let's move to and see how this builds into an actual working space. In OMI, we progress in really clear steps. We start with a simple finite address line, what we call a basic nibble point. That point then opens a sphere. Inside that sphere is our local tetrahedral centroid frame, which then validates into a completed incidence block. So a simple data point beautifully blossoms into a validated projective space.
This yields an absolutely crucial canon statement for the protocol. The centroid is the unit. The sphere is the carrier. The tetrahedron is the first exact relation. I really want to emphasize here that the centroid is not just the average of some floating XYZ coordinates. Actually, scratch that. It's more like an immovable incidence anchor that rigidly binds the whole tetrahedral block together.
All right, section 4, finding pi without pi. This brings us to the real climax of this explainer. If constants are just projections, how in the world does pi naturally emerge without ever being programmed into the system as a stored value? To see the magic trick, we introduce the Polybius square. This is a 4x4 grid displaying a hexadecimal field from 0 to f. In the Ohm protocol, this finite geometric address field is where two crucial central diagonals essentially compete against each other.
These diagonals create a completely deterministic chiral situation. Both diagonals are fully capable of reaching a perfect mathematical closure, both through XOR operations and through sum operations. They are basically perfectly matched competitors facing off on this finite grid. Because both diagonals can reach closure, the geometric direction of our space becomes a literal race. If the D plus diagonal wins, we get a forward posting outcome. If D minus wins, we get an inverse outcome. A tie means it's balanced, and if neither completes under bounded digestion, the relation is simply incomplete. So, the crucial point is this. Pi is not a foundational protocol authority. It does not need to be stored in the computer's memory to make a circle. Instead, pi is merely a projection witness of this exact chiral closure event we just looked at. When that finite diagonal race is finally rendered onto your screen as an angle, pi naturally appears. Pi is the receipt, folks, not the rule.
Section 5, the Fano plane receipt. This reliance on receipts brings us to Ohm's ultimate fraud detection system. Before any pixel is drawn, the system needs to know the geometry is mathematically legal, and it does this using the smallest finite projective plane, the Fano plane. It acts as a compact receipt governed by incredibly strict properties. Exactly 7 points, exactly 7 lines, exactly 3 points per line, and exactly 3 lines passing through each point. It is rigid and it is perfect.
These are the non-negotiable rules of point-line duality. If a computer checks a geometrical structure and the numbers don't perfectly match this strict point-line duality, the OMI protocol immediately rejects the geometric space. It detects the fraud and stops cold before it even attempts to draw a single line on your screen.
Finally, Section 6, relocating mathematical constants. Ultimately, OEMI proves that through incidence partitions, like the BQF partition equation, 60x squared plus 16xy plus 4y squared, constants like pi and phi haven't been banished. They've just been relocated to their proper fields to act as verifiable receipts. I want to leave you with this provocative thought. If fundamental constants, the very numbers we thought built the universe, are really just downstream receipts of a deeper valid relationship, how does this change the future of computational reality? If we no longer have to fake reality with floating point guesses, what entirely new flawless digital universes can we begin to build? Think about it. And hey, thanks for exploring this with me today.